Welcome back. Have you ever wondered if it's possible to include faster than light travel within general and special relativity? Stay tuned in this video. I'll explain my ideas of how we can do this. It's helpful to draw an analogy between faster than light travel and something that we're familiar with. Let's consider a jet airplane. In this case, I have an animation here of the F-18, and it's flying along at supersonic speeds. We can draw some similarities between a spacecraft that would be traveling at faster than light speed. So one, the aircraft, in this case, has thrust, and that's what's pushing the plane forward. We then have the aerodynamics, and simply aerodynamics is just the flow of the air or fluid as it flows over the structural body of the aircraft. Now we can characterize the aerodynamics with the density of air and the fluid pressure. Now as an aircraft exceeds past the speed of sound, it creates a shock wave at the sound barrier. In a similar manner, let's consider a spacecraft capable of faster than light speed. In this case, we'll assume that we have a propulsion system that's producing thrust, and treat space-time as though it's filled with a type of fluid. And just like in the case of an aircraft, this vacuum fluid will flow around the spacecraft, and I'm going to coin this hyperdynamics, which just simply means how the geometry of space and time will flow around the spacecraft as it exceeds the speed of light. We'll also assume, just like in the case of an aircraft that reaches Mach speed, that it produces a shock wave or a sonic boom. We're going to assume that as the spacecraft exceeds the light barrier, it's going to create a light boom or a shock wave in that case. So we're going to draw similar analogies to an aircraft traveling through the air, just like a spacecraft traveling through space-time. Now, of course, we can't push the analogy too hard, but it's useful in looking at it conceptually. I'm going to give a very brief introduction into general relativity and special relativity. So we want to know we need a set of coordinates to tell us where we're at in space and where we're at in time. So there are three spatial coordinates. We're going to call these X, Y, and Z, and then we have time that will give us our position as well as where we're at any given time. So here I have a spacecraft, and it's going to be orbiting around the Earth. And so in order to know where its position is, we need to know its position as well as time. Now we can code the three spatial positions and time into what's called a four-position vector. Now we can take two four vectors and combine them together to get an absolute distance between different reference frames. And so this is done by using a little mathematical tool called the metric. Now the metric is just a simple way that takes two four vectors and combines them into a single absolute distance in this case. And so we call this the line element. So you can think of the metric as a glue that takes these two vectors, combine them together to give us an absolute distance. Now, each observer is going to have measure distances differently relative to the rest frame. So by combining them together, we can get what's called an absolute distance, which both observers must agree on. Now, from the line element and the metric, we can develop a generalized Lorentz gamma factor. This Lorentz gamma factor is used to translate information from our length and time, and I've explained this in other videos. So when I'm in a spacecraft or an aircraft and I'm traveling along, my measurements of time and distance are going to be different versus somebody who's sitting in a control tower. Now, in order to transmit information from my moving reference frame to the control tower, we need the Lorentz gamma factor and coordinate transformations in order to tell us how different measurements are made in different frames of reference. So let's consider I'm in my aircraft here, I have my oxygen mask on, and I'm transmitting my distance and time to aircraft or to air traffic control on the ground. They're going to see me on the radar scope, and they're going to be using light signals and radio signals, basically radar, to determine my position, location, and time. Now, these time and length are going to change relative to the speed I'm traveling at. The closer we are to the speed of light, the slower my time or the slower my clock will be as I'm near the speed of light. The length will also contract relative to my speed to the speed of light. If you recall, time dilation tells us as a clock travels closer to the speed of light, it slows down. And then for faster than light clocks or tachyon clocks, they will reverse themselves and go backwards in time, or at least that's how they will appear to a stationary observer. Also, length contraction. As a ruler travels closer to the speed of light, it will shrink, and then as it exceeds the speed of light and goes faster, it will stretch out and become longer and longer the faster it goes. In my previous videos, I go over in a lot of detail of length contraction and time dilation, and I suggest the viewer go check those out to get a better understanding of it. Primarily in this video, I'm going to focus on how we can incorporate faster than light travel within special relativity and general relativity. The question now becomes, how do we describe faster than light travel within special relativity and general relativity? We do this through the metric. I developed a line element that will allow us to smoothly transition the light barrier to achieve faster than light speeds. And this is the line element here. On the right side, we have just the Minkowski line element for flat space, and I've multiplied this by a transition function. So the entire Minkowski metric is multiplied by a scalar function. The transition function is dependent on the velocity that you're traveling at. This transition function allows us to smoothly transition below the speed of light across the light barrier, then to faster than light travel. If you want more details on the transition function, check out my previous video on episode 1 and 2. I go into a lot more detail what exactly the transition function is. In this graph, I plotted the hyperbolic tangent function. When the velocity is less than the speed of light, we get 1. When it's nearly equal to the speed of light, we get a slope of a line. And then when it's faster than the speed of light, it approximately equals -1. Now recall, we can generalize a Lorentz gamma factor and have it based on the metric, which combines our two velocity 4 vectors together. Let's imagine that our spacecraft is traveling one-dimensionally. So we'll consider the velocity in the x direction and the velocity in the y direction to be 0. And we'll only consider a one-dimensional motion. The Lorentz gamma factor for my particular line element is simply the square root of the transition function multiplied by the classical Lorentz gamma factor that we find in special relativity. Here we see that when the velocity is much less than the speed of light, the transition function is approximately 1, and we get what we expect, the classical Lorentz gamma factor. When it is approximately equal to the speed of light, we essentially get a constant term that's dependent on the temporal coefficient. And the temporal coefficient determines the transition rate crossing the light barrier. When we're faster than the speed of light, the transition function is -1, and we get what I call the tachyon Lorentz gamma factor, which describes how clocks and rulers will behave when we're traveling at faster than the speed of light. Now graphically, we can see here we have a clock that starts from rest, accelerates up to the speed of light, it begins to slow down and then reverses itself as it travels faster than the speed of light. For the length contraction, we can see that our ruler, when it's below the speed of light, starts to shrink. It reaches a minimum length at the speed of light and then begins to stretch out as we travel faster than the speed of light. Hey, thanks for watching my video. Don't forget to hit the like button and the subscribe button and comment on what you think of my theories below. Taking two 4 momentum vectors, we can combine them together using the metric. This will give us an absolute notion of energy and momentum. Each person will have their own measurements of what momentum and energy are. So we need to be able to combine them together so that each observer in their different reference frames can agree on that exact value. So here in this case, we combine them together and we can see we have our energy, and then each of our spatial momentum vector components of our vector are combined together. For simplicity, we're going to assume that our momentum in the x direction and our momentum in the y direction is 0, and we're only dealing with one-dimensional momentum along the z-axis. After some fancy algebra, we come up with an equation that tells us how our momentum changes relative to velocity. Using our approximations for our transition function, we can define 3 different classes of particles. We can define bradyons, which are particles that travel less than the speed of light. We can define luxons, which are basically photons or any massless particle that travels at the speed of light. Then we can also define tachyons, and tachyons are particles that travel at faster than light speeds. Now we can plot an energy versus momentum graph. And you can see here we have our bradyons at the top of the screen. We have our photons, and they travel at 45 degrees along the axis. And then we have our tachyons that travel on a hyperbolic path. So basically, bradyons and tachyons mirror each other around the photon. Now, instead of taking the limits of our transition function, let's plug in our transition function and see what happens. The transition function allows a bradyon to cross over the light barrier to become a tachyon, and vice versa. We can have a tachyon transition the light barrier to become a bradyon. Now, from our energy and momentum equations, we can pull those apart and we can define our energy as well as our relativistic momentum. Again, we're going to assume one-dimensional momentum, so we're only going to consider motion along one axis. After some algebra, we can come up with 2 new sets of equations. One is a dimensionless equation that has the relativistic energy divided by its proper energy. The second is relativistic momentum to proper momentum. And from these equations, we can show how the energies and momentum transition the light barrier. Taking our ratio of relativistic energy to proper energy and using the limits of our test function, we can define 3 regions for the particles. Once again, the bradyons are traveling inside the light cone, and they can't exceed the light barrier. And then we have our photon, and then as well as the tachyon. So there are these 3 regions: bradyons, luxons, and tachyons. Now, including the transition function, we can see how a sublight particle, a bradyon, can transition the light barrier and then continue on to faster light speed. This gives us a ratio of different energies in these 3 different regimes for our particle as they travel through space and time. Now, let's consider momentum versus its speed. Here, this is a slightly different graph that measures primarily the momentum of the particle. And again, we will just apply our limits, first of all, using the transition function. And we get, not surprisingly, the classical relativistic momentum for the particle, which is a bradyon, or particle that travels less than the speed of light. we get a photon, and then of course we get the momentum versus velocity of a tachyon. And just like before, we'll plot this graph again, but include the transition function this time, and it shows us how our momentum versus velocity can smoothly transition the light barrier. So in all three graphs that I presented here, the takeaway is that this transition function allows us to smoothly cross the light barrier. Now, the entire transition function is dependent on the value of the temporal coefficient. So we're going to make an estimate to determine what this temporal coefficient is and what its value is. It basically determines the rate of change crossing the light barrier. For a very large value, we're going to get a rapid and sudden transition. For a smaller value, we get a much smoother gradual transition across the light barrier. To approximate the temporal coefficient, we're going to assume we have a particle of mass that's traveling near the speed of light. Now, we'll assume that we have the energy to do this, and that the upper limit on this is going to be the Planck limit. Now, the reason I chose the Planck limit is because that's the point where special relativity and general relativity may no longer apply, and we have to turn to a quantum gravity theory or possibly string theory to determine what happens, but we'll just use it as an approximation. So let's set the relativistic mass equal to the Planck mass, and we're going to divide that by the mass of a proton. So we're going to assume that our test particle, the proper mass is the mass of a proton, and we can see that in this approximation that the temporal coefficient must be 10 to the 38th, which is a dimensionless value. Now, I've just barely touched on how the metric is used in special relativity. The special relativity is valid when spacetimes are relatively flat and we ignore or we say that the curvature is negligible. But for a full analysis, we have to turn to general relativity, where curvature is not negligible and may play a significant role. So Einstein's field equation, we see here that G is essentially a geometric component that describes a curvature of space-time. On the right, we have the stress energy tensor that tells us how much energy is needed to curve space-time. Then we have the cosmological constant that tells us whether we're working with a vacuum energy system, and that can be either positive or negative. Now, there are three parameters for the cosmological constant. It can take on a positive value with a negative isotropic pressure, which creates positive curvature. We call this a de Sitter space. Furthermore, we can set the cosmological constant to 0, and we'll call this a neutral vacuum state, and this is basically a flat space. The last state that it can have is a negative state with positive pressure, and we call this an anti-de Sitter space, or a space that has negative curvature. To help visualize the cosmological constant, let's imagine we have a box of particles in it, and in this box of particles we have blue particles and we have red particles. Now, let's say that the blue particles represent a positive energy vacuum. And so what this means is that that's all the normal matter around us. It's the Earth, it's the attractive forces that it exerts on each other. So we can imagine that this volume wants to shrink and pull in on the surrounding matter around us. This will create a positive curvature and a negative isotropic pressure. Now, the cosmological constant was used by Einstein to come up with solutions that will describe the expansion or contraction of the universe. If the cosmological constant is positive, this means that we live in a closed universe. Now, one way we can tell if we live in a closed universe is that if we got in our rocket ship and we zoom all the way around, it's something like a sphere. So a sphere represents a closed curvature or a closed space-time. meaning that if we start at one location, we zip around, we will come back to the same location that we started at. Now, if the cosmological constant is 0, we have basically a neutral vacuum state, and that the Minkowski space is flat. If we were to zoom across in a straight line in our rocket ship, we would just continue forever and never would come back to where we started from. And we can also say that our space, that the amount of red and blue particles is about the same, and so that the pressure is equalized and neither contracts nor expands. If the cosmological constant is negative, that means that we live in we will have a positive isotropic pressure, and we call this an anti-de Sitter space with negative curvature. This tells us that we would be living in an open universe that would expand forever and ever. And as scientists have studied and looked out at supernova and other things, they have determined that we possibly live in an open universe that will continue to expand forever and ever. Here in this example, or in this picture, we have a hyperbolic surface, and if we lived in a closed universe, it's represented by a circle. If it's a flat universe with zero curvature, then we're going to get basically a plane. And if it has negative curvature, then we are talking about two hyperbolic shapes that sit on a saddle on this hyperbolic surface. A few notes on Einstein's curvature tensor. He developed this to describe the geometry of space-time. So basically it tells us how space and time will bend and be curved by matter. So here in this animation you can see we have a heavy object like the Earth, and it bends space down, creating a positive curvature. As space-time bends, it tells matter how to move. So there's this sort of duality between bending space and telling matter how it will move. We now need to plug in our line element into the Einstein tensor to determine what kind of geometry we have. Now we have to modify the transition function because it was dependent on velocity. And working with velocity in general relativity doesn't make a lot of sense and is kind of cumbersome when making the calculations. However, we can apply a coordinate transformation to make things a little bit easier in our calculations. Since we are dealing with velocity squared, we can equate this to an equivalent parameter, which is basically 2 times the acceleration times the change in distance that the object is traveling. Basically, this is just the classical kinematic equation. I'm just applying it here as a coordinate transformation. Doing so takes us from a velocity space to a spatial space, and the parameter is only dependent upon the amount of acceleration that is being applied. In this case, I'm going to assume that the acceleration is constant and doesn't change throughout my analysis. So now we can write the transition function and have it depend on our spatial coordinate z. Here I defined a parameter called alpha, which it has units of inverse length, and it's simply the acceleration divided by the speed of light squared. And you can see that we can apply it to our metric, and our diagonal components are just simply 1 over the transition function. Now let's take our metric and we'll plug it through the machinery of the Einstein tensor. So we basically load the data up, put it on a computer, and out spits a bunch of differential equations that we need to solve. Here are the differential equations that we got after we running it through the machinery of the Einstein tensor. Basically, 3 of the components are identical to each other, and the spatial component along z is the only one that differs. Otherwise, everything else is 0. Due to symmetry, we can simplify our calculations quite a bit by just simply contracting on one of the indices and looking at the trace of the metric. Next, we need to plug in our derivatives for the transition function, and they're presented here in this slide. And I'm going to simplify the derivatives by taking our transition function and having it equal to a hyperbolic function divided by a normalizing factor. Our simplified curvature tensor now looks like this. With the Einstein tensor, this defines our hyperdynamics. And hyperdynamics, once again, is just how space and time respond to an object that is traveling through it. Just like aerodynamics changes according to the geometry of the aircraft as it's traveling through the air. The next thing we need to talk about is the stress energy tensor in the Einstein field equations. Now, the stress energy tensor simply tells us what kind of energy we need to have in order to bend space and time. Now, the stress energy tensor is composed of several components. We have the energy density, we have the momentum density, the shear stress, and pressure, momentum flux, and energy density. Now, for my analysis, we're only going to focus on the diagonal components, that is the energy density and the pressure, and we're going to assume a vacuum solution for our analysis. By assuming a vacuum solution, we're assuming that all of space and time are filled with a fluid that behaves quantum mechanically and can never be eliminated. Now, this fluid is going to exhibit two properties. One, it has energy density, and the second is that it exhibits a pressure on the surrounding objects around it. The stress energy takes on this form of equation for an ideal fluid, where we have the energy density and the pressure of the fluid. Now, we can assume that we can inflate it or deflate it, just like Wile E. Coyote here can be inflated or deflated depending on how much air he pumps into a balloon. Here we have the equation for an ideal fluid. Now, let's assume we have an observer that is traveling along with the fluid. Then the velocity for vector term, we only need the first position, so we'll ignore the rest of them just to simplify calculations. So by taking the contraction of the stress energy tensor, we can get a form that's pretty well simplified, that only depends on the pressure of the fluid, the energy density of the fluid, and the transition function. We're now in a position to find solutions to the Einstein equation. So plugging in all three components, we have the geometric component that tells us how space is curving to allow for faster light travel. We're going to take the cosmological constant and we're going to consider a negative curvature in this case. And then on the right side of this equation, we have the stress energy of the fluid. Using the magic of algebra, we get a simplified form that looks like this. And recall that the transition function has the following characteristics. It's 1 below the speed of light, relative constant at the speed of light, and then a -1 when we exceed the speed of light. As a check, let's verify our initial conditions. So let's assume that the rocket is at rest. What do we get? Turns out on the right-hand side is essentially 0. If we consider that the cosmological constant is also 0, we basically get the classical result of perfect fluid, which basically states that the energy density is equal to 3 times the pressure for the vacuum. An interesting case is to consider what happens when our spacecraft reaches the speed of light. So in this case, we're going to say that the critical distance, which is ZC, is the distance that is transversed by the time we reach the speed of light. So that means that the transition function is equal to 0 and that the warp factor or the velocity is roughly equal to the speed of light. So this leaves us with 2 equations. The first one has the geometric term then the cosmological constant, and then the pressure of the vacuum fluid. The second question has the energy density plus the pressure of the fluid, for which we can solve for. The second equation presents us with a problem. If we require matter to be positive value, then this implies a negative pressure is acting on our spacecraft. One way around this is to assume that the pressure is negatively valued, making a positive pressure and thus a positive energy density that we are dealing with. So going back to our first equation, which describes the geometric component and the cosmological constant, we thus change the sign of the pressure, giving us a positive value. Next, we can solve for the temporal coefficient, which is a function of our alpha parameter, the cosmological constant, and the pressure of the vacuum around the spacecraft. Now we need to interpret our results here. Now, if we assume that the pressure density is 0, then we can directly relate the cosmological constant and the temporal coefficient as our initial values for for the physics that's involved. Interestingly enough, if we set the acceleration on order of the light speed square, we find that the initial value of the cosmological constant is 10 to the 76, which is a rather large value. Now, this leads to a problem in physics. When the cosmological constant was initially used to determine what kind of universe we live in, whether it's static, whether it's open and expanding, or whether it's going to close in on itself. Now, I think that this may solve the cosmological problem, because on the one hand, we calculate a very small value when we look at cosmological models, but then when we calculate and quantize electromagnetic fields, we get a rather large value. And I'm not going to go into a lot of detail on the cosmological problem. Lots of other videos out there that explain it. But the interesting thing is that with my model, you have initial value for the temporal coefficient, plus there's this extra alpha term which contains acceleration in it. Now, it seems that we can calibrate this to match cosmological models. So it may be that the cosmological constant isn't really a constant, but is a function of acceleration and the speed of light squared. One way to interpret alpha is to think about a region of space that has a bunch of particles in it. These particles have a net amount of energy, and then when we apply a force to that area, we can take the ratio of the force to the proper energy, and that gives us our alpha term. So as a review, let's go back to our analogy of an aircraft traveling through the air and a warp ship traveling through space-time. Now, in the beginning, I suggested that these two analogies are similar. At least it helps us to conceptualize the process that's going on here. So if you recall, we have thrust, which is pushing the aircraft through the air. When it reaches the speed of light, it creates a shock wave around the sound barrier. And the flow of air around it is determined by the engineering and aerodynamics of the aircraft. And we can characterize most of this through the fluid density and the pressure of the fluid. It may be possible to manipulate the temporal coefficient. Going back to our equation where the spacecraft is traveling near the speed of light, we have lambda naught. And if we have a negative pressure that is acting against it, we may be able to drop this value, and thus making it easier to cross the light barrier. One way to think about it is that we're trying to hike up over a mountain. We need a certain amount of energy to climb to the top of the mountain to be able to go down the other side. If we're able to peel back the top of that mountain and we're going to hike over a smaller hill, then it would, of course, require less energy. So it may be possible to build some kind of device that lowers or changes the temporal coefficient. Now, I haven't altered the fact that the speed of light is still the speed of light. I've simply shown that through this equation, it may be possible to lower the temporal coefficient and requiring less energy to cross the light barrier. Hey, thanks for watching my video. Don't forget to hit the subscribe button and the like button. If you have any comments on my theory or a critique on how I can improve it, or if there's something I did wrong, please leave it below in the comments section. I also have published a book with all the gory detail and math involved. If you'd like to take a look at it and read through it, I'll leave a link in the description. It's available on Amazon.